Hello dear students, this is our 10th lecture on these tensors. So in our previous lecture we have discussed about how to calculate these matrices, mm, if these spherical polar coordinates, or you talk about the cylindrical coordinates, or even if you talk about these rectangular or Cartesian coordinates, right? So the matrices will be different in different because so we should have this length should remain invariant if you go from one frame to another frame of reference, right? So this was what we have discussed in our previous lecture. So today's lecture is on, that is, if we talk about now space-time interval. So if we talk about now space-time interval. So we need to discuss. So in today's lecture, we need to discuss about the space-time interval of this metric tensor. So the space-time interval. So that means, so you know that if we write that length in this Euclidean space or in three-dimensional space, we can write that dxi will be equal to, so that's dx. You can write that dx, this will be equal to, okay. So this is our this length element in this in the three-dimensional space. Now, if you talk about now, if you write this the length element in four-dimensional space, right? So that means you are writing now the length element, the four component of that length element, right? So let us represent that again, that dx with mu. So mu starts from, or so mu goes from, that is 0, 1, 2, and 3. So that means mu equal to 0 corresponds to our that time component, and these are axis, this 1, 2, and 3 corresponds to our x, y, and z component. So that's why it is called that it's called a four component of that length element, right? So this you can write now. So now it has four components here, right? So you can rewrite this as, so this will be equal to that dx0, or you can write that c dt dx, okay, or this will be equal to, okay. So that means, maybe in one of my lecture I have discussed that dx1 corresponds to a dx, so that means that, right, and dx0 is our cd, and this, okay. So that means I can rewrite this as, so this will be equal to, you can write this as, right, so this is our dx. So you can write this is the four component. So first one corresponds to our that time component, and this is our space, that x, y, and z components, right? Now, if you go from, so this from the theory of special relativity, we can say that, so from this str, right? So that means from special theory of relativity, we can say that our dx prime mu square equals to dx. So that means if you go from one frame to another frame, so this remains invariant. So maybe if you remember, so if you if you have watched my those previous videos, so we have written that ds square prime square equal to ds square. Right? Okay, so this length element, square of the length element remains invariant because you can add that dx in terms of that. So you can so this should remain invariant if you go from one frame to another frame. Now let's rewrite this stuff. So this is if you talk about some from this special theory of relativity. So dx prime mu should be equal to this square of that. So I can rewrite this as, so this term I can write as, so this will be equal to, because this is the dx, that is c dt, right? Now I'll write here instead of dt, I will write d tau. Okay, right? And this dx mu square I can write as, because x mu, you're writing that it has that time component plus that space components, right? So you can write that time component, this will be, because this is dx mu square, so this will be c square dt square minus. Okay, so from this equation, so from A, so if you use this A equation, right? So because, so you may raise a question why I am writing now, because of that this dx will be some dc dt. So why I am representing here d tau here? So tau basically it represents our proper time. So proper time, so it is that time which remains invariant, which remains same which remains same between the two frames of time. So if you go from one frame to another frame, right? So proper time, so it is independent of the choice of the coordinate system, because if you go from one frame to another frame, so this tau it remains same, that time remains same. So that time is called a proper time. And similarly, we have another that is dt. So this is our improper time. So it may change. So this dt it may change if you go from one frame to another frame, right? So this is how you can write. So from the theory of special relativity, we are saying that ds square should be equal to ds prime square. So we can write that this c d tau should be equal to this, right? Okay. Now if I rewrite this, so rewriting this equation, so that means I can write that. Okay. Or you can rewrite this as, so this will be equal to that c dt, or you can rewrite this as, okay, so you can write that. Okay. So you can raise a question why I'm writing it in this way, because so this is our that this is our again that matrix G mu nu, but it is called a Minkowski matrix because it contains now it's a 4x4 matrix, right? And it will this if you insert this G mu nu here, so this should be equal to this one. So if you expand this term, because our mu runs from some 0 to 3, that is 0, 1, 2, 3. So similarly, we can say that this dx mu it runs from some 0 to 3. Okay, so we can rewrite this as c d tau should be equal to this one, right? So that means this g mu nu should be, so this g mu nu, so that's our it's our Minkowski matrix and it's formula. Okay, so this is the form of the matrix, and this matrix is called so this matrix is called. Why I'm writing this? So this is our Minkowski matrix because we are working in now four-dimensional space. That's Minkowski space. So that can have the time component, time as well as the space component. So that means we are working in the four-dimensional space. So that means the form of the matrix that I am writing here. So it should be some 4x4 matrix, right? So it is not necessary that you can write G mu nu in this way. So you can take them instead of that you can write that first minus then rest will be plus. So it is one and the same thing. So that means this notation is called a plus, or you can use this notation also, minus, plus, right? So it is because one should be, because otherwise you cannot have that ds prime square should be equal to this, right? So this is mandatory. So because when you multiply this matrix to this term, so you will get all these components, right? Because if you put that g00, I will expand that. So I will at some point I will evaluate this and you should get the same thing, right? So my present discussion is about this tau and t here, right? As I already told you, this tau is our that it is called. So this tau is basically it is called the proper time, right? And this is independent. So that means this tau is our proper time and it is independent on the choice of the coordinate system, right? And let's now write this. If you write now, suppose in my previous lecture, if I write some vector, if I so for time being, you just remember this thing. So at some time, at some point, I will evaluate this. I will get the same thing here, right? Now I'm saying that if I have some vector, so how if you to transform this vector from some one frame to another frame, so how it gets transformed? So if you are writing now, if I have some vector A in some private frame, so that's A prime alpha. So if you want to transform it some another frame of reference, so that means we have some the same vector but it is in some beta. So that means I am transforming this. So that means we should have some transformation matrix, right? And that transformation matrix will be okay. Or you can write this as right. So this is how it gets transformed. Because if you put that alpha prime equal to b beta, so that means you will get a alpha prime should be equal to a alpha prime, right? So this is our that transformation matrix. So this transformation matrix is similar to that our Minkowski matrix, right? And in some books you may observe that this g mu nu it is replaced by eta mu, right? So in order to distinguish from some rest of the tensors, so sometimes it is written as this eta mu nu also. That's equal to plus minus delta mu nu. Huh? Right. Now, so my question is now, so that means for any vector, if we have any vector, so we can write that vector. If you want to transform that vector from some one frame to another frame, so it should transform like this with some transformation matrix and this over that canonical delta, and you should get the same value, right? So that means now instead of that, if you write down the velocity, so similarly you can write for the velocity vector, right? So we can write that if we have that velocity now, we can write that v prime mu, so that should be equal to, so we can write some another phrase that is v mu, and this will be partial x prime mu. Okay, so this is clear because if, so here, so I already showed you that our a prime alpha is this one, right? Or a prime alpha will be this one, right? And similarly, you can write for this one also. So that means a prime will be should be this one, right? And this is that transformation matrix, or you can write it in terms of that canonical delta also, right? Now, if you write now, you can write now what is our this x mu here. So x mu equal to, so this four components of that displacement, so that's equal to, okay. Now if you want to calculate, so this is the displacement as you can see from my previous lecture. So this is, or in the previous slide I showed you that x mu we can write it this way, right? Now this is our this four component of that displacement or length element, you can say that. Yeah? Now if you multiply by, or if you calculate its velocity, so you can, if you write now that partial by partial t, x of mu. So that's equal to c. Okay, because when you differentiate it with respect to time, so this is our improper time, right? Okay, so this is our that so this is our that velocity. You can write that this is some u mu. You can write, so that's equal to some c and some v vector. Okay, because v is that ux, uy, and uz, right? And so what basically tells us that, so if I transform this velocity vector from one frame to another frame, right? So this velocity will change here because so earlier one was that was c dt, now it is c. So that means c changes here, right? So that violates the basic postulates of special theory of relativity, because we know that so one of the postulate of special theory of relativity is that velocity of this c, value of c remains invariant, remains same irrespective of the frame of reference. If we go from one frame to another frame, but c is changing here, right? So that means we cannot transform it this way, because I am basically observing here. If you see, it is variation with respect to some improper time, but improper time, as I already told you, so that depends upon the choice of the coordinate system, because it can change from one frame to another frame. So that means instead of taking its derivative with respect to this t, so we will take this derivative with respect to some scalar, sorry, with this proper time tau, right? So because as I already told you that proper time, it is independent on the choice of coordinate system, because it is same for all the frames of reference, right? So that basically gives me the characteristic, right? So instead of that, I can write this as, so you can write that, instead of that, you can write this as, so you can write them. So our u mu will be equal to. So we can define it this way. Okay. So I can define this velocity u mu. So for velocity as, so that's equal to. You can write that partial x mu. Okay. So can we define it this way, right? Okay. Because so this, so we can write it this way using chain rule, right? Because this is not a 4 vector. So in general, you are saying that a vector, so it should transform so that the value of c, it should remain invariant if you go from one frame to another. So it should transform like we have those equations like these Lorentz transformation equations. We have that if we go if we make this translation along x, we can have that x prime will be equal to some gamma into x minus vt. And similarly for t time, you can have that gamma factor, that Lorentz. Now, what I am saying here, so this is not a vector because it doesn't transform like those Lorentz transformation equations. So that means we need to, so we can write this as this u mu as that's partial x mu by partial t. So you are taking it using the chain rule. We are dividing by this d of tau, and tau is our proper time, right? Now, so this basically forms. So you can derive this as, so u mu will be equal to. So this will be equal to. So this will be equal to, okay, because this will be our v mu, some velocity here. So I am representing it by v, so it is different from this, right? Okay. Right, or you can rewrite this as, because so this should be our this term, it should be our gamma factor, that logarithm factor, because मैंने आपको already बताया कि 4 vector they should transform like what how these according to these Lorentz transformation equations. So if you make translation of this coordinate from some so that x prime goes like that gamma times that x minus vt, right? So it should transform like that, because that remains invariant. So that also preserves that these basic postulates of this special theory of relativity. So one of the postulates that is violated by this one, that c doesn't remain constant, right? So if C doesn't remain as constant, so it violates the basic postulate of special theory of relativity, right? So C should remain same, right? So in order to preserve that, preserve those conservation laws, or you can say that the basic laws of this special relativity. So we are writing that in terms of this one, but so it should be like that gamma times some mu. So that means this should be our gamma, right? So let's calculate its value. So we can rewrite this as, so we know that, so from this, from SR, or you can write from STR, so we can have that C d tau square equal to, that's equal to, okay, so we can have this, okay, right. So this is how that, so you can have that ds prime square equal to, okay, so we can write it this way, or you can rewrite this as, so this will be equal to, okay, uh, so what I wrote here, or you can write, that's it, huh? Or if you multiply now, so because we need to calculate, so in previous slide, so what we are interested in calculating this term, huh? So this one, so which term, that is dt by d tau, right? So हमें ये चाहिए dt by d tau. So that means I can rewrite this as, that is c square, or you can write this as, so, let me write here. So I did a mistake here, so let me write from here. So instead of that, I can rewrite this as, okay. So you can rewrite this as, so this is c square dt square, right? You can write this as, can take now dt square common. Okay, so I simply take that dt square out, right? And inside that is c square, this one. Okay, or this will be equal to, okay, or you can write that, because I need that dt by d term. So dt by d term will be, So this is our that Lorentz factor. So you just check because so we need this thing. Huh? So because dt by deta is equal to this one, right? And this is nothing. This is our Lorentz factor because we get that. So dt by deta. So deta by deta is our. So that is our this thing, right? So uh, that is equal to 1 divided by square root of 1 minus c square by c square, right? So we can rewrite this. So this is our that gamma. Okay, that's our Lorentz factor. Okay, so we can rewrite that. So what will be u mu then? Because our u mu equal to so our u mu equal to v mu into that is dt by deta. So that's our gamma. So that means u mu will be equal to v mu into gamma, right? So we can rewrite that our u mu will be equal to that will be gamma times v of. Okay. So now this is a four vector because we have some that Lorentz this Lorentz factor here, right? So it will transform like those these LT transform this Lorentz transform, right? And this is a four vector, right? So that means if you write any vector, if you transform like this, so that's called a four vector, right? Or like this is a velocity four vector, or you can have that acceleration four vector. So if you want to transform the four components of acceleration, right? So that should transform like this, gamma times some a of some mu here, right? So coming back, so you can rewrite this term as so this will be u mu, or you can write this in component form. So that is gamma into c into some v. Okay, because because mu takes those values, mu takes that 0, 1, 2, and 3, all those values. So mu equal to 0 comes that comes over that c dt, and this is our dx dy. So that's c, right? So this is our you can write this. This is our that 4 velocity. So that this 4 velocity transform like this, right? So earlier definition. So that was some. So if you remember that, so u mu it was transformed, but this is not a 4 velocity, right? Because we don't have any so that Lorentz factor, right? But this is a 4 velocity. That u mu it should be gamma times c into v, right? Now, instead of that, let's have a look on. So this is let's have a look on this space-time interval. So before that, you can rewrite this as okay. Now let us calculate now. So as I already told you, so let's calculate that ds square. So I can write now. So let's have a look on space-time. So let us have a look on this space-time interval for this Minkowski space, right? So we can write that we already know that our ds square is equal to that is g mu dx. Okay, so this is clear, right? And you can rewrite this as so you can rewrite this term. तो इस term को मैं लिख सकता हूँ that g mu nu dx nu. So as per the Einstein summation convention, you can write this as this. So this will be equal to dx. Okay. So this is as per this Einstein summation convention. Okay. So I will explain maybe in next lecture. So what is this Einstein summation convention? But for time you just remember that. So if you write this dx nu, so this nu and nu they will contract, right? So you get dx nu, right? Okay. So this is simply contraction, simply that you are taking the product between the matrices. If you take, because G mu, you know the form of this G mu, it can be that 1 0 0 0 minus 1 0 0 0 0 minus 1 0 and 0 0 0 minus 1. And similarly, if you talk about this dx mu, right? So because mu is a 4 vector, so it has 4 components, you are basically taking the product between the matrices. So contraction, you are simply taking the product, right? So this is our, this mu and mu will contract, so this is dx mu, right? So that means our dx mu equal to, okay? So let's calculate first the time component, because I told you that we need to calculate that space-time interval, right? So that means time component as well as the space component. Yeah, space component, then time component for this Minkowski space, right? So let us first write for mu equal to 0, right? Again, mu में 0 होगा, so it gives me that dx 0. So that will be equal to, okay? So because we need to put that mu equal to 0, so this will be dx 0 and g mu 0 to dx 1, right? Now, so how possible, what are the possible values of this mu? So it can take that 0, mu equal to 0, 1, 2 and 3, right? Because we know that, so this will be equal to that g, okay? So this will be g0 0 because first पहले हमें लेना है mu equal to 0, so this will be g0 0, mu equal to 0, dx 0. And similarly, when you put mu equal to 1, यहाँ पे भी 1 आएगा, यहाँ पे भी 1, because already mu equal to 0, right? And similarly 2 and 2, yes. Okay. Now from our this matrix, we know that we have this. What's our G mu? Right. So our G00 is first component. So this will be that 0, 1, 2, and 3. Right. So this will be 0, 1, 2, and 3. Okay. So G00 will be this one. So that means our G00 equal to 1. Right. So ये values आएंगे यहाँ पे, because G00 is 1, G11 is -1, G22 is -1, and rest odd diagonal elements will be 0, because अगर हम लेंगे G02 will be 0 or G12 will be 0, all those odd diagonal elements will be 0. Only the diagonal elements will be non-zero, and first will be that 00 will be G00 will be +1 and rest will be -1. It's not necessary, you can take the reverse of that. So you can take the time component minus, then space components will be positive in that case, right? Okay. Now, so let's rewrite that. So you just check that. So we have this G00. G00 will be +1. So only this component will survive, right? So that means we can have this, that dx 0. Okay. So that means you can write this as, so this will be equal to CD, right? And similarly, if you write that, because our dx nu equal to that G mu dx mu here, right? Now you put mu equal to 1, you'll get that dx 1. because when you put nu equal to 1, so this will be g mu 1 dx nu. So this will be take the all possible values of mu, so you can get that g mu 0, or what I wrote here. So this will be g 0 1. Okay. So now because this g01 will be 0, so only g11 will be here, that will be minus 1, right? So that means we'll get that dx1 equal to minus times dx, right? And similarly, okay. So we have calculated, these are basically the components. So यहाँ पे मैंने we have, so first component we are getting that positive, rest we are getting the minus negative, right? Or if you take its reverse, so then this will be negative, rest will be positive, right? So these are basically the superstar components of this interval for this Minkowski space, right? And similarly, if you write now, so what about this? So you might have seen that, like if you have a look on this expression, like we have this expression. What it indicates is that, so that means dx1, the subscript, and dx1 on the superscript. So these are basically duals of each other, or duals, I can say the reciprocals of each other, right? Like if I have two vectors, so if you remember that, okay, so before that, so that means this is our that Minkowski matrix. So Minkowski matrix. Now instead of that, अगर हमारे पास, if you talk about this, if we have this Euclidean, that some in Euclidean geometry you have those pseudo-Riemann geometry you can have this matrix. जो वहाँ पे जो matrix होगा, so it will be that plus plus plus. Right? So this is the this matrix for this. You can talk about that if you have this in Euclidean geometry, right? So we can have matrix, but all will be positive. So this is the main difference. If you talk about that pseudo-Riemann geometry with this space-time interval, right? Now, so as I already told you, so if you have a look on this expression, so this, so dx1 is minus dx1. So this indicates that these are basically duals of each other. So that means dx subscript 1, that is basically reciprocal or duals of that dx superscript 1, right? So if you remember that in one of my lecture I talked about that if you have those vectors in quantum mechanics, so we can represent them in terms of those bracket notations also, right? So we can rewrite them. So like if we have this ds square, we can write that or ds square. So that's equal to. So this I can write as dx into dx. So I can write this way also, right? Or this is equal to that g mu, and these are basically duals of each other, right? So this is basically the cat of this dx and this is the velocity, right? So that means cat and bra, these are basically duals of each other, or these are said that complex conjugate of each other, right? Because that's clear, right? Like so you can in general you can write, so suppose we have some vector, so that means अगर हमारे पास एक vector होगा, in general I can write that in this four-dimensional space, we can write it in this form, that is g mu a mu, right? So in general you can write. So this is basically, or you can write this as, or you can take the contraction, because so this term gives you that is a mu b, right? So you can write it this way also. So that means this you can write in this form. Okay. So or you can write, because if you take this product, so this is basically if you talk about this four vector, so you can have those, you can have this a0 b0, then that space component. Maybe we'll discuss that in coming lecture. So this is basically how you can write these matrix tensors or space-time interval of this matrix tensor as well as this spacetime interval, these components of this spacetime interval in this Minkowski this space, right? So I think I should stop now. Maybe in the coming lecture we'll talk about these some duals and some contravariant and covariant vectors. What are those vectors, right? Thank you.